Okay, so we'll ask our next speaker to come up. So the next talk is a climate data record for the terrestrial water and energy cycles, and this will be given by Eric Wood. He's a professor of civil and environmental engineering at Princeton University. So Eric, how do I move it forward? So there's the big button there, and then you can use this if you want to use the pointer.
Okay. Thank you very much. Howard, thank you very much for inviting me to this wonderful event. I couldn't remember what I said I was going to talk about, so, but this will fit in very nicely, I think. You'll notice that in the top there's Princeton University. There's also Princeton Climate Analytics, which is my new startup. So it's consistent with what we have done here. So the workshop theme that was out there was to reflect on developments over the past 40 years. I don't know quite why. You haven't worked for 40 years yet, have you? So I didn't know you were that old. I thought you're quite a young man. Excellent. So you really want to know, you asked us, what's really transformative in the last decades? What's the evolving research topics to extend these advances? Those are problems that Howard and I will never get to. Ever-increasing focus of mine that I'm going to spend a fair amount is how society can access and benefit from our research advances, something which I called when I gave my Wegener lecture in EGU, Research for Society. And it's really climate services, which I think is a very important area to help us. So I'm going to talk about two things: developing global observations and advancing an information computer systems that allow to make integrated water information available easily to society. The third one, which I often talk in this, when I think of advances, is development of process-based land surface models, but there just wasn't enough time. I think there's some very innovative things there that could happen. Development of data sets for diagnostic studies. If you think about users today, they need to have time-consistent data sets over the historical climate period for climate monitoring and forecasting, short-term, seasonal, and future climate projections. And the real challenge, those are all coming out of different sources, and a real challenge is to make them all consistent so that you can do things, if you're Munich Re or you're Goldman Sachs or whoever, to do long-term risk analysis and to understand change in the right context. So programs that supported the development of these, and there's a number of them, and I just put a few of them up. Here, historical climate analysis. This happens to be the MEASURES project from NASA. There's also one for NOAA. NOAA has a similar program. Climate modeling, there's the climate forecast system and other things from NCEP, ECMWF. There's others which are doing these. Now you could probably put in here the Copernicus program from Europe. And then, of course, there's the CMIP activities on future climate projections. And if I press this, we've taken all those, and we have, in fact, developed long-term consistent data sets. If you go along the top, you can see the forcing data, reanalysis, gridded observations, remote sensing. You get weather forecast models, seasonal climate models, global models. And they all get downscaled and merged to be consistent. So you have to worry about consistency among them and across them. And they feed, in fact, a variety of application models, whether they are some hydrologic models, there's some hydraulic models, or crop models, impact models, and what have you. So this is where you start to create information. The people who are interested at this level would like magic, to get all of this input. They don't want to do all that work. And in fact, I would claim that most people in this room, if you're over 50, have no idea how you would get CMIP data and make it useful. But they would have someone that would do it. And if you're under 25, you can do it quickly, and if you're in between that, you would do it slowly. And that's part of the problem. And then, of course, there's products like flood and drought, sectorial impacts, 7-day forecasts of floods, and there's all sorts of indications down here. And so if you look at these as columns, historical reconstruction, real-time monitoring, short-term seasonal, and climate projections. And my group has probably spent 15 years putting all this together. So from a scientific perspective, what are the questions that a seamless water cycle data system could answer? And you can start down in the bottom here, looking at, are the data suitable for benchmarking and monitoring? Are they, what's the variability and trends of the global water cycle, including extremes? Do we understand the mechanisms of initiation and the persistence of extremes? What's the uncertainty in future climate projections, and at what spatial scales is monitoring and prediction needed? And so these all tie together. You can see issues on data sources. You can see things on mechanisms between the historical analysis and monitoring, risk impacts, mitigation, and adaptation. There are many PhD theses that are tied up in trying to unravel that and apply that. And so if you're under the age of 25 and you don't have a topic, there's probably some that you can think of there. We've used this to look at the global water cycle, and what this is that from some reanalysis we can get some convergence information. We have some discharge in green from our land surface model, VIC, and we have P minus E from a variety of precipitation data sets and evaporation data sets. And if you look at all of this, you see that things look pretty interesting. They should all be the same. For some reason, the ERA interim is very small in this region here. But overall, you can see that you get the global land, you can, in millimeters per year, about 260, plus or minus around 10%. And so that's an example of one of the things. This is one of the great things that GWEX wanted to do. And if you look at this with sea flux, which is this, the overland's land flux, sea flux, is the ocean part, runoff, convergence, closure, precipitation, evaporation from sea flux and from land flux, and the closure, you can close it down to a couple of percent as it turns out. And yes, it is true that averaging hides a multitude of sins, but it's still pretty impressive that we have numbers with some error bars that are down at that level. And here's the residual part, and you can see some places it's a little bit higher, some places it's a little bit lower. And if you did the same thing with this, with reanalysis, they'd be an order of magnitude or more worse. That reanalysis, in part because of the lack of closure and other things, just doesn't do a very good job. And then there's other things, there's trends. So here's another interesting problem for the young people here. Net radiation is going down, okay? People say there's more clouds, there's more aerosols, there's more water vapor, so it shouldn't surprise us it's going down. And the surface is getting hotter, so there has to be more upward long wave radiation. So you can see the upward long wave is increased quite a bit because the land surface temperature has gone up. And the temperature gradient between the near surface and the ground is going down. So the question is, what does this tell us about the acceleration of the water cycle? It's something that we've struggled over on trying to figure out how does this fit in. And you talk to people and say, oh, evaporation is going up. Well, what's happening to sensible heat? I don't look at sensible heat. I only look at evaporation. So they haven't tied the water and energy budgets together very well. And I think that that's another problem that Howard and I will never get to. And it says something about the variability of the trends. And you can see here in the net radiation. You can say, well, I'm going to look at these in situ stations because there are these in situ data sets that are there. It turns out that all the places where there's big trends, there are no stations. So that's always a bit of a challenge. I think FluxNet only exists in the United States and Europe and a few over in Japan, and that's about it. And the radiation stations are not well distributed. So it's a real challenge to go and take these data sets to do that. I'm going to talk about, so that's basic data set and how you can use it for science. I'm going to talk about something which I've talked about before, and hopefully University of Saskatchewan is going to solve the problem. Advances in information and computer technology. Why aren't students taught high-performance computing? I get all sorts of postdocs. Of course I know how to compute. I use Excel spreadsheets, and I use MATLAB. Oh, but I can use MATLAB and Python, so therefore I guess I know how to use Python. And the truth is, you need to be able to handle terabytes of data in scripting, parallel computing. At Princeton, we're lucky to say, these are the sort of public, student-accessible systems. We're talking about ones which have thousands of cores. Here's one, 10,000 cores. We have very fast systems, and students, at least my students, get sent off to learn how to use that. And I think that's a big issue because you can't develop big data systems unless you know how to use that. So let's look forward. So that's my complaint about for the faculty in this room that aren't making their students do this. So looking forward, what are the problems that we have to focus on? How do we build legacy models and data systems? What are the compelling problems of interest to society? And this leads to this research for society, and I have a few things to say on that. Because I think it's really important. We all get funding from the government. We all get funding from different places. But there are lots of places in the world where the capacity is limited and the needs are great. And I think that we need to respond to that. And we've done a lot of work for many years with UNESCO in doing that. But before I get to that work, I want to talk about other problems. We heard just now about water and the globalization of food. So I won't say anything more from what Richard said. But here's some reports that have floated across my desk. Water scarcity, Ernst & Young, water security, World Economic Forum. No, Howard, you didn't invent water security. There's lots of people who've been looking at this. But you have certainly built an incredible research program to try to address it for Canada. And here's an interesting speech given by Mark Carney, who's the governor of the Bank of England, who's a Canadian, in fact, on climate change and financial stability. He got about it 50% correct. He had the climate change part mostly about temperature, but he didn't have the water security part that is very important in this speech. But it is very interesting, the people who are talking about this, and they can't get the data. So I think there's a new age of water and climate information. There's a global water cycle, there's water security and economic activity. There is the need for developing a global water information system. And they all tie together, especially that the people on the water security and economic activity need the data sets to do the sort of analysis going forward. We have built a regional and global monitoring capability. Richard showed our stuff from Africa, the deserts. We've done Latin America. These were built for UNESCO. These will be, they're run at quarter degree. They're going to be updated to 5 or 10 kilometers in a few months. They have forecasting, they have seasonal forecasting, they have all sorts of things. We run the United States at either 3 or 4 kilometers in real time. And we'll do the whole world, we're about 90% done. So it is important to build these systems so people can use them easily. You don't want people to have to struggle to get the data so they can do the problems that they really want to work with. And so there's a whole dashboard in here where you can download data, you can do animations, you can do forecasting, you can do a bunch of different things in there. What's been quite exciting is that we have what I call the data model integration challenge. We have a client who has 350,000 basins in this domain, and they have some models that they like to use. And our data system that we developed for them is 100 terabytes, I think I got that, gigabytes, terabytes. It's a lot of data. I think it's 100 terabytes, making it impossible to load into their system. And so the solution that we're going to offer is a cloud-based data service, an API that links the data to the models, to the applications, or for scientific analytics. And this, they're only interested in this part, and they need the other part. So you can see, have all the data sets, the database integration, the catchment extraction. It goes into what they have developed as their model interface that produces what they want to do. And this ease of building these systems is the only way you can have users who aren't highly sophisticated users, i.e. they're under 30 years old and they can do what we want done, to actually do that. And I think the challenge for WMO is, their Hydro SOS, is in fact to make it easy for users, besides the fact they'll probably have it closed and no one can use it, like many of their other systems. So we've built a dashboard. You specify the downloads, basin selection. They have their own basins that they do, model inputs, submit the data requests, and out it comes in the right format. And in fact, you can click on something and we build dynamically the basins that feed into that. And so that, we think, is a very good solution for the cloud data service. And I think that that's what we have the capability to provide into there. Here's another one. Little tiny basins, they go down to about 25 or 50 kilometers. So this is, this allows the users to focus on the problem, generating alternatives and analyzing solutions, and not spending forever trying to build these data sets. So my takeaway message is the complexity of current research and applications, and there are many climate change, intersectoral impacts, modeling from process understanding to policy, water, food, energy, security, there's a whole host of them out there, requires updating and remaking our research tools. And what I mentioned today is mostly the seamless data systems, exploiting big data and making the hydrometeorology easy to use, and they can focus, the users can focus on the hard problems, which is analyzing the solutions. So lots to do, lots of interesting problems, hopefully lots of smart students. And Howard and I will be watching from the sidelines. In fact, I'm waiting for Howard to invite me to go sailing with him in Turkey, but I've yet to have heard that. So, but we hope it'll happen.
Okay, great.
Okay.
Thanks. Thanks. So the only one exception I have with what you said is I don't think you and Howard will be on the sidelines. I suspect you'll be right in there with everybody else. But so any questions for Eric here? Sorry. Oh, there you go. Yeah. Jeff, you got the mic there?
Just hidden.
Thank you, Eric. There's some wonderful and huge amount of work, of course, to get it all integrated together. One thing I remain curious about, how would we validate the outcomes of the results of this model? I know there's tons of things to validate, like colorful maps and results. You're using VIC, I assume, but what's the challenges for validating the outcomes?
Well, individual components get validated. We have a new data set that has been published in the scientific literature, has been compared to other data sets. You know, that's the same way you validate science, okay? There's lots of users who've spent decades building their models, and they have confidence in their models, but they have trouble getting the data. And so, you know, whether their models are good, whether their models are bad, whether they're indifferent, is a different issue. But if you want to do the scientific part, you'd validate it exactly the same way that you would validate any other work.
Thank you.
Okay, any further questions for Eric? Or? Thanks, Eric.
Okay.
That's great.